Hello and welcome to Talking Papers, a podcast where we talk about papers and let the papers do the talking. And today we will be talking about SampleNet, Differentiable Point Cloud Sampling. And with me is the first author, Itai Lang. Itai, can you introduce yourself?
Hello everybody, and Itzik, thank you for having me today. My name is Itai Lang. I'm a PhD candidate at Tel Aviv University, advised by Professor Shai Avidan. And I will talk about SampleNet. This is a joint work with Asaf, Manor, and of course Shai Avidan.
This paper was accepted to CVPR 2020 as an oral presentation. So in a TLDR format, 2-3 sentences, what is this paper about?
Okay, so the paper is about learned sampling of point clouds, and it is achieved by a novel differentiable approximation of the sampling operation, which basically is non-differentiable.
Let's go to the introduction section. So what problem exactly is this paper addressing, and why is it an important problem to solve?
The paper considers the problem of data selection. And sampling is a highly important operation in processing in general and in point clouds specifically. It enables to reduce the computational demands. For example, save memory, reduce the computation time, reduce bandwidth when transmitting and receiving the point cloud, the data. And sampling can preserve much of the processing power. But the question is how to sample the points. And you do sampling not for the sake of sampling, but for purpose, for a downstream task. So the question we asked ourselves is how to learn to sample. And if you think about it, there is no supervision. There is no one that tells you sample these points or another one. And what we did is learned a task-oriented sampling in order to select the points that are contributed the most to the subsequent task. And a key challenge was to overcome the non-differentiability of the sampling operation, because sampling is like a step function. Either you select a point or not. And what we did is approximate the sampling in a differentiable manner to enable the learning of a sampling model in an end-to-end manner.
So let me just take a step back here, okay? So basically what you're talking about is point clouds, which are basically points sampled on shapes, right? So it's either you have a mesh that you sample points on, which is like the synthetic case, or you have an actual scanner somewhere in the world scanning objects, right? Yeah. Now we have those bunch of points, but maybe there's so many points, it's very expensive to process. What you're looking for is basically a way of just finding which points are important for any or some downstream tasks.
Yes, for example, let's say you have a point cloud that you would like to classify, but there are too many points and you would like to use less points. So the idea is to reduce the number of points while still preserving as much as possible the performance of the task.
So what is the main contribution of your paper?
Okay, so we have several contributions. The first contribution is a novel differentiable approximation of point cloud sampling, and it is achieved by an operation that we call soft projection, and I will elaborate later. Second is that we show improved performance in comparison to other sampling alternatives, either classical non-learned sampling methods or recently proposed learned methods, and we show a substantial boost in the performance with sampled point clouds. And additionally, we apply our sampling method for a new task that was not considered before with learned sampling, which is the task of registering 2 point clouds to one another. And this is a challenging task because the same sampler should be consistent across 2 different point clouds, a source and a template point cloud, for a shared downstream task. So we applied also our sampling model to this task and show improved results.
Okay, so moving on to the related work section, which papers are most relevant to the reader of your paper?
So there are two main papers that should be read before reading our paper. The first one is Learning to Sample. This is actually our work, our first work, 1 year before the work of SampleNet. And in this work, we propose to learn for the first time, similar to SampleNet. In this paper, Learning to Sample, we show that one can learn how to sample. However, in this paper, we did not deal directly with the non-differentiability of the sampling operation and offered a workaround instead. In this work, in SampleNet, we dealt specifically with the sampling operation and made it differentiable and showed substantial improvement in the performance of tasks with reduced number of points in comparison to the work learning to sample. And additional paper that is relevant is farthest point sampling. This is, I think, the most common method nowadays to subsample point clouds. And this is a classical method that do not consider the downstream task. It optimizes a geometric objective such that the sampled point cloud covers as much as possible or almost uniformly the original point cloud. And we show that we can do better than this approach.
Yeah, like many other new learning-based tasks, right? People used to do it in an engineered way. Now you do it in a learned way. It works better.
Yes, of course.
Okay, so let's dive into the approach. What is the key idea and innovation of your paper, and how do you do it?
The key idea and innovation of the paper, as I said before, is to approximate sampling in a differentiable manner, which enables to learn a task-specific sampling model for a subsequent task. Now, suppose that you are given a task that embodied as a neural network. For example, a point cloud classification network, such as, let's say, PointNet, which is very famous and ubiquitous. And let's say that this network was trained on complete point clouds with n points. And now assume that you would like to apply this task, this model, on a much smaller number of points. Let's say m points. And the question is, how would you select m points out of n points such that you preserve most of the task performance? And with the numbers that we work with, we found out that the number of possibilities to select m points out of n points is more than the number of atoms in the universe. So there are many ways to sample a point cloud, and we asked ourselves, how should we do it? And this is where SampleNet comes into play. It takes the original point cloud with n points and outputs a simplified point cloud with m points. Now, a simplified point cloud is a point cloud with m points, which are not guaranteed to be a subset of the endpoints. But we are interested in sampling. We would like to pass on original points that were recorded, let's say, by the sensor from the original point cloud. This is where the other part of the model, the soft projection, is taking place.
So hold on, before we dive into the soft projection, let me just recap for a minute, right? So you have a downstream task, let's say classification, right? So classification, it means you get an input point cloud, you want to output a label, right? So this is a point cloud of a person, this is a point cloud of a car, this is a point cloud of an airplane. Yes. Now, this input point cloud has a certain number of points, let's say 10,000 points. And what you're asking basically is, how can we choose out of these 10,000 points, or not even choose, but how can we create like some subset of points, which is much smaller? So let's say 1,000 points, 100 points, that we would input it into the same network and get as little degradation in performance as possible, right? Correct. That's your question. Right. And the way you do it, right, is you do it with that soft projection thing.
Yes, of course.
Going to explain right now.
Yes, of course. So I elaborate a little bit more. So let's say in the pipeline, we have the original point cloud, SampleNet, and then a sampled point clouds, and then the task network. This is the pipeline, okay? So SampleNet is implemented also as a neural network, that it takes the input point cloud, the complete point cloud with n points, and then it regresses a smaller number of points. It regresses the coordinates by a learned neural network to m points, to a much smaller number of points. But as I said, these are not guaranteed to be a subset of the original points, and we would like to keep the fidelity of the sample data to the input data. So now we would like to convert the simplified point cloud to let's say we would like to project the simplified point cloud onto the original point cloud. And let's say we can, the straightforward approach to do is, let's say, to take each simplified point cloud from the output of SampleNet and look for its nearest neighbor from the input. However, it is non-differentiable, because once I select a point from the input, it is non-differentiable anymore because it does not depend on the network parameters. So what we did, instead of nearest neighbor selection, we applied the novel operation that we propose, which we call soft projection. And how does it work? For each point in the simplified point cloud, we look for the k nearest neighbor from the input point cloud. So let's say we have a simplified point that the SampleNet regressed, and then we look for its k nearest neighbor, its local neighborhood from the original point cloud. And now we replace each simplified point with a softly projected point, which is a weighted average of the local neighborhood of the original points, where the weights of the weighted sum are determined according to the distance from the simplified point, which depends on the network parameters, to each of the neighbors in the original point cloud. And additionally, it depends on the temperature parameter. So now we have a weighted average where each original point is assigned a weight according to its distance, where a closer point gets a higher weight, scaled by a temperature parameter. Now, the temperature parameter is a key to the soft projection operation. When we lower the temperature, like a simulated annealing, the weight distribution for the neighbor points become closer to a delta function, and thus approximate the selection of a point from the input in a differentiable manner. During training, we add the temperature coefficient to the overall objective of the training, where the overall objective contains also the objective of the task network and the objective of sampling, which requires the sample point to cover the input point cloud and also to have closer points from the input. So during training, we minimize the temperature and thus approximate the sampling in a differentiable manner and can learn the sampling model in an end-to-end manner. And this is how we achieve learned sampling.
Let me recap this. That was a bit much. Okay, so basically your sampling pipeline works like this, right? You have your input point cloud that you want to subsample, right? And then you have your output point cloud, which is your what you call the simplified point cloud. So for each point in the simplified point cloud, you find the k nearest neighbors in the input point cloud. And basically what your network learns is a weight of each one of these nearest neighbors, or you would say that your output simplified point is the weighted sum of those k nearest neighbors, right? Now, these weights are learned by the network with your temperature parameter that when approaching zero, that will be the delta function. So that basically means it shows a single point.
Yes. And another way to look about it is the following. Let's say that regressing points that are important to the task is hard because the regression is done in the 3D ambient space. Okay, but if we take the simplified points, which do not need to be that exact, and then replace them with already existing point from the input point cloud that we would like to select from. So we replace a regression problem, a global regression problem of points with multiple local classification problems where each simplified point should be classified, should be attributed to one of the original points in the point cloud. And this is a much simpler problem. So you are already close to the surface of the original shape because you select a weighted average from its original points. And the only thing that you need to do, you need to put the simplified point close enough to the original point that you would like to sample, and then the temperature coefficient, which is minimized during training, will bring you closer to this original point. And this is the intuition why this soft projection operation improves the performance with respect to regressing the points for the subsequent task, because it's a much easier task and it is built in within the architecture of the network.
What is the loss function here? What are you optimizing then? So you have the temperature loss, which you want to push the temperature to be as low as possible. But what else?
This is the one part of the loss. We call it the projection loss. We have another loss, which is the task loss. So we would like the loss of the task when it is applied to the softly projected point cloud to be as low as possible. Let's say if we talk about the classification as an example, so we would like the prediction vector of the network when applied to the softly projected point cloud to be as close as possible to the one-hot vector of the correct label. So the idea is that we would like the loss, the performance of the task, to be preserved as much as possible when applied to the sample or to the softly projected point cloud. And another loss is the regularization of the sampling. Let's say the simplification loss. We would like, let's say, this is a coarse. This loss requires that the simplified point cloud is coarsely covers and close to the original point cloud. Let's say it's a variation of the chamfer distance between the original point cloud and the simplified point cloud, which requires that each original point has a close simplified point, and each simplified point is close to an original point. And the temperature coefficient is like a fine-tuning of this coarse simplification, which requires that the simplified point is not only close, is actually very close to an original point, and it is achieved by minimizing the temperature. So this is the overall loss: a simplification loss, a temperature loss, which relates to the self-projection, and the task loss.
So would you say that the simplification loss ensures coverage of the shape? So it kind of prevents everything from focusing on maybe one specific region?
Yes, it acts as a regularization loss, because if we do not use it, let's say the sampler could code the selected points instead of sample the points. Let's say if we not regularize the simplified points to spread over the original point cloud, so the model can choose that if we have a chair, so all the points will be at the bottom of the chair. And if we have a car, so all the points will be at the front of the car. And if we have an airplane, so all the points will be at the sides of the airplane. And then it codes its output instead of learn the actual sampling of the point cloud. Mm-hmm. So this is like a regularization of the sampling model.
So just to recap, 3 components. One component pushes the temperature to be as low as possible. So the soft projection would be kind of a delta function. One loss keeps the task unaffected, so tries to keep the performance of the task the way it was. And one regularizes everything and tries to keep kind of an even sampling or prevent it from coding
from overfitting.
From overfitting.
Yeah, of course. Yeah.
Okay, so let's talk a little bit about the results. So how do you even go about evaluating what is considered a good sample?
Imagine a graph where on the x-axis you have the sampling ratio, and as you traverse through this axis, the sampling ratio is increased, and it means that the number of sampled points is decreased. So you have a decreasing number of points on the x-axis, and on the y-axis you have the performance of the task. So with sampling ratio of 1, it means that all the points are selected. So you have the original performance of the task. And as you increase the sampling ratio, you would and decrease the number of sampled points, you would like the graph to keep being as high as possible, as much closer to the original performance of the complete point cloud.
You're basically evaluating the sampling quality based on the task performance quality, right? So as you reduce the points, you want to make sure that you still have the same performance on the task.
Yes, of course. And for the running example of the classification, we would like the instance classification accuracy of sampled point cloud to be as close as possible to the original classification accuracy with the complete point clouds. So the graph would look something like a decreasing graph, and we would like the decrease to be as low as possible.
And just to make sure, so during training, you're not touching the original classification architecture, right? You're just tuning the sampling part of it. So basically, you're feeding to the same network that was trained with, 1,000 points. Now you're feeding it 100 points or 128 points or even less. And you want to keep the same performance or as high performance as possible.
Yes, correct. So we assume that the task network is given, it is already deployed, and we keep it fixed. And what we would like to do is we add SampleNet as a front before the task network, and then optimize the sampling model to be task-oriented, to be as good as possible for the downstream task. And then we evaluate the performance with the same network with less points. And it has another benefit. It disentangles the influence of the sampling operation of sampling on the task performance. Because if we would retrain the task network and the sampling network and get an improved performance, so it is hard to tell from what element the improvement came. So we assume that setting of a pre-trained task network and train SampleNet according to the given task network.
Yes, and in this setup, you're basically keeping the task inference time fixed, right? You're always giving it a constant input, and then the inference time for that is fixed. And you're actually maybe even reducing that compared to the original training of that task network, right? Because now you're feeding it 100 points instead of 1,000 points, so you made everything much faster.
You're correct. So we keep the network, the task network fixed during training and of course also during inference. And regarding the computational demands, we show that we can achieve a reduction of 90% of the compute operation with the increase of 6% of memory, because we need another memory space to store the sampling model in addition to the task model. But the sampling model is simpler than the task network. It has less parameters, our sampler. So overall, when the sampler is applied to the original point cloud and the task is applied to the sampling point cloud, the overall computational operations is much less in comparison to applying the original task network to the complete point cloud.
Okay, so we've been talking this whole conversation on the classification task, but you also tried this on the registration task. So can you explain what is the registration task and what's the performance there?
We applied SampleNet to several tasks. One of them is the classification, as we talked about. Another one is the registration task, also point cloud reconstruction, and even point cloud retrieval. So let's talk about the point cloud registration task. What is this task about? Assume that you have 2 point clouds. One of them is called source and the other is template. And one of the point clouds is rotated with respect to the other point cloud. And each point cloud is an instantiation of the same object, not necessarily with the same points. We would like to compute the rotation parameters that align the 2 point clouds to one another such that they are overlapped. This is an important task because when you have a scene and different sensors view the scene from different locations, so you would like to align the scene to have a complete scene. What we did, we took a registration network that consumes the source and template point cloud and outputs the rotation parameters, and we added SampleNet, the same SampleNet in front of this network, and the same SampleNet samples the source and the template point clouds. After that, feeding the sampled points to the registration network, and we would like to get a correct rotation parameters to align the 2 point clouds. And as I said before, this is a challenging task because the same sampler operates on 2 different point clouds and should be consistent, should sample consistent points in order to enable the registration task. And regarding the results of this task, we measured the rotation error, and we found that for sampling ratio of 32, which in this sampling ratio only 3%, about 3% of the original data points are taken, we cut the registration error of FPS, which is the classical sampling method, by half. So we much improve the performance with the same number of points, but selecting them differently results in an improved registration performance. Now,
okay, let's recap that, right? You take a third of the points.
Not third, 3%.
3%.
Yes.
You take 3% of the points, and you get, compared to traditional furthest point sampling, you get a 50% improvement in performance.
Yes, and the degradation with respect to using the complete point cloud is only about 1 degree. It sounds like a good deal to me. We saw a very interesting behavior of the sampler. We applied the sample for different categories of objects, and for example, for the car category, we saw that the sampler prefers to select many points on large flat regions. Let's say the bottom of the car. So it takes points on these regions, which are powerful for registration, and we believe that this is why the registration succeeds, because it has large two planes which are easy to align to one another. And another very interesting finding is that, as we talked before, the farthest point sampling optimizes the geometric objective and tries to sample the point cloud as uniformly as possible. And what we saw is that SampleNet do not sample the point clouds uniformly, but rather non-uniformly. So it learns to select the points that contribute the most to the task, which is not a uniform distribution over the point cloud. And these are the points that actually improve the task performance with less points in comparison to the classical method of farthest point sampling.
Yeah, that's actually interesting. So basically what you're saying is that uniform sampling, well, we could have guessed that, right? But uniform sampling is not the best way to sample points for any task, right? So the balance between that term in your loss that pushes it to be more uniform and I would say the task loss kind of fight each other. They're competing, and basically what you're saying is that the final result shows that the task loss is a little bit winning because the output is not uniform, but I mean, you still cover the shape, but the sampling is not uniform. You have more points in important regions of the shape. Okay, so do you want to quickly cover the other tasks that you tested this on?
I'll cover the reconstruction task that we also applied the SampleNet for. So in this task, we have a point cloud that we would like to reconstruct. We would like to encode and decode. Let's say that we would like to reconstruct the point cloud not from the complete input, but rather with a lower number of points. So what we did, we fixed the reconstruction network that usually takes the complete point cloud, encodes and decodes it to the original point cloud, and sampled a much lower number of points. And if you think about it, we created an autoencoder which takes the original point cloud, samples it to a smaller number of points, and then the task network upsamples it to the original point cloud. So we have an autoencoder where the latent vector is also a point cloud. And the difference with the regular autoencoder is that usually you have a latent vector which may be hard to interpret, but here we have also a point cloud. And we see the points, we see the coordinates, and we can understand how the reconstruction network works and which points are important, are distinct for upsampling or reconstructing the point cloud. So it was also interesting to work on this task. And another interesting finding is again, with sampling ratio of 3% of the point, we can reconstruct the point cloud with an error factor of 1.34. So the error is increased, the reconstruction error is increased by only a factor of 1.3. We measured the normalized reconstruction error, which is the reconstruction error when the task is applied to the sampled point cloud, divided by the reconstruction error when the task is applied to the complete input point cloud. And visually, the reconstructions are very similar. So we can use 3% of the point and still reconstruct the point cloud. Let me comment about another interesting behavior that we found during the work on SampleNet. So we talked about that we use a temperature coefficient and minimize it during training in order to have the weight distribution over the original points in the weighted average of the softly projected point. We would like it to be as close as possible to a delta function. So we minimize the temperature during training, and you may think that the temperature is reduced closer to zero in order to get the weight distribution over the original point very close to a delta function. But what we found out that the temperature, it minimized to the extent which is good for the learned sampling within the sampling pipeline, which includes the sampler and the task. And it is not a delta function, but there is a distribution of weights across the original points. And as an ablation study, we tried several things. We tried to minimize the temperature more with not a learned temperature profile, but rather a handcrafted temperature profile. And we saw that the performance degrades. And even we added a cross-entropy loss on the distribution of weights for the original point, for one hot vector for the point with the highest weight. So we got a weight distribution which is much more closer to a delta function, and the performance decreased.
If I just put it in my own words, you're basically saying that from your experiments, you saw that it's actually not good to get a delta function because it basically chooses one point and sticks to that, right? It's most often the closest point to that simplified point. And that's actually not too great because maybe that point is not positioned in the right location. Then it's actually good to give it that soft constraint to maybe move it between the neighbors to find like that exact location that's mostly beneficial to the downstream task.
So you do not want to decrease the temperature too much and too quickly at the beginning of the training, but you would like the system to minimize it with its own pace, which is most beneficial to the learning process. And then we saw that it is best to delegate the minimization of the temperature to the learning process and to get the best performance possible.
Do you think there's a right way to initialize it in such a way that the first temperature you start off with is actually something that's better, right? Because this is just a scalar per point. I guess you start with, random weights, which gives you like a random temperature, but maybe it's interesting to think about, is there a right way to initialize in such a way that you will get a better starting position for the temperatures?
If we didn't try it, another thing to try is also we use the same temperature for all the simplified points for the projection. And another interesting thing is maybe to have an adaptive temperature per simplified point.
Mm-hmm. All right, conclusions and future work. How do you see the impact of the paper so far and going forward?
There are several follow-up works that we saw. One of them is our work from our group, which is called the DPC, unsupervised deep point correspondence via cross and self construction. And in this work, we took the self-projection operation and extended it to the latent space. So this is one extension. And another extensions that we saw in the literature are unsupervised point cloud co-segmentation. In this work, the authors took two sample nets which compete between one another, where one should sample the points, the object points from the scene, and the other, the foreground points, and the other sample net should sample the points from the background of the scene. And they compete in order to sample all the point cloud of the scene, where each sampler should separate the foreground or the background from the scene. And if you do it on multiple scenes, so you get co-segmentation of an object, let's say a chair, from a scene with clutter with the background points. So this was very nice to see that someone actually took SampleNet and applied it in another framework.
This way you get like kind of different samples, because for background and objects you have different things that are important, right? So it makes sense to try to sample them with different, maybe even competing sample nets.
Yeah, that's exactly what they did. The sample nets competed each other, and they were tasked to learn to select different points, mutually exclusive subsets of points from the original scene. We're combining the two sets of the sample point cloud. You should get the original scenes.
Okay, moving on to my favorite part of the podcast. What did reviewer 2 say? So please share some insightful comments that the reviewers made during the review process, maybe even the ranks if you feel comfortable to. This helps a lot new PhD students that, are now facing their first rebuttal or review process. Please share your review.
I can say that the reviewers were very kind. I can tell you one comment, the summary comment of one of the reviewers, which was very thrilled to read. So he said, "This is a novel paper with excellent results, advancing the state-of-the-art results in many tasks. The paper is well written and extremely well executed, with many details and justification of engineering choices." Reading a review like this I feel like it is rare, and I'm so glad that the reviewer understood the paper and shared the same belief of ours that the task of learn sampling of point clouds and proposing a differentiable sampling operation is important, and this is what he wrote. He or she, sorry.
In the review process, even when we like a paper, we don't always write it flat out. This is a good paper. We believe in it, right? Sometimes we're just too busy finding flaws that even if we like the paper, we don't always write this summary sentence that just is so important for the student or person who did the research work. And this is actually very, very important in the review process.
And on the other side, one of the reviewers didn't like the term soft projection. And he didn't understand why we call it projection and why we call it soft. And unfortunately, he gave a less favorable review. If I can say something about the rebuttal for new PhD students, and not only for the rebuttal, but for a resubmission if needed, I think that when you do research, when you do your work, so go with your technical truth, with your belief in your in your work, in your paper. And finally, the paper got accepted in the first submission. And the first time that we submitted the paper, it got accepted. And
so you managed to convince the reviewer. Yeah, actually, there is a paragraph in the paper that kind of explains why you called it self-projection, why it might not be trivial or projection in a traditional sense. And I really like that because I can see why the reviewer found this term confusing. And I can also see why it's actually a very good term to describe what's going on. So that extra paragraph really made things clear to me.
And my message is, even if the paper is not accepted on the first round that it is submitted, you not necessarily need to revise all the paper according to the reviewer's comments, because this reviewer did not understand the term, the soft projection term, but the other ones did understand. And what I'm trying to say is go with your truth, with your belief. And if you need to resubmit, so I think one should take the essence, the important comments from the reviewers. Let's say if a comparison is missing or another experiment is missing, and focus on these parts, not necessarily terminology parts or things that are less important.
Thank you very much. All right. Sure. Okay. So thanks for being an awesome guest. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.